What is RLHF? RLHF, reinforcement learning from human feedback. This is a technique that has become very popular, specifically because OpenAI says they use it to fine-tune their ChatGPT models. So we're going to be looking at a blog post here on HuggingFace that explains what RLHF is. So let's get started. Right here in the title, fine-tuning. This is the process of taking a machine learning or deep learning model, right, that has been trained for a long time on a data set, and then training it for a little bit longer on a different data set, right? So fine-tuning is within the sphere of training machine learning models. 20B refers to the fact that there's 20 billion parameters. Machine learning models have different sizes. LLMs, a large language model. This is a type of machine learning model. This is the machine learning model that is behind all your favorite tools such as ChatGPT. Google has their own one called Palm. Meta, previously Facebook, has their own one called Llama, and so on. 24 gigabytes, this is basically memory. So a GPU is a graphics card, and GPUs have different amounts of memory. And the bigger your model is, the more memory you need on your GPU to fit it. So I suppose they'll probably go further in this, but 24 gigabyte GPU is definitely not casual. This is over $1,000 for sure. But it's still consumer GPU. A lot of times, machine learning research uses GPUs such as A100s, which are significantly more than this 24 gigabyte. So without further ado, let's go ahead and dive into this. We are excited to officially release the integration of TRL with PEFT. So these are probably Python modules, Python packages specifically for fine-tuning in RLHF. To make large language model LLM fine-tuning with reinforcement learning more accessible. So reinforcement learning is a type of machine learning. It predates deep learning. So people were doing reinforcement learning way before we had neural networks or anything that looked like that. The kind of platform upon which reinforcement learning is built is this idea of a Markov decision process, which is this idea that you can basically describe the world as a set of states, and you have agents that take actions in states and produce more states, and then you can have observability of those states. So it's kind of almost like a mathematical framework that allows you to think about problems and problems where there's an environment that rewards you for successfully completing things. In this post, we explain why this is a competitive alternative to existing fine-tuning approaches. So, of course, we can expect that the authors of this paper are associated with whatever these modules are, and they're going to try to convince you that this is the only way to do reinforcement learning and fine-tuning. But there is nothing really that proprietary about RLHF. There are lots of open source reinforcement learning frameworks, and reinforcement learning with human feedback is much more about the human feedback part and what data set you choose to fine tune with, rather than how the RL is actually done. PEFT is a general tool that can be applied to many ML use cases. Okay, if you want to directly deep dive, check out the scripts over here. Cool. LLMs combined with RLHF, reinforcement learning with human feedback, seem to be the next go-to approach for building very powerful AI systems such as ChatGPT. This is a little bit misleading. The very powerful AI systems, such as ChatGPT, the reason they're good is because of the original training data and the fact that they're very big. So 99% of the intelligence of a large language model such as ChatGPT comes from the original training that was done, to usually with something simple like next token prediction. RLHF, reinforcement learning with human feedback, is really about things like AI safety and making sure that the output of these LLMs is specifically what you want for some task. So it's not required, and I actually suspect that in the future we'll find that RLHF potentially even hurts large language models, right? Much like transfer learning leads to this problem of catastrophic forgetting, where if you take a classification model that's been trained on cats and dogs and then you start fine-tuning it on turtle classification data, it's going to perform worse on the cats and dogs. And there's probably some kind of analogous situation happening with this RLHF, where by fine-tuning a model on these kind of constructed human feedback data sets, you're probably reducing its ability to generalize a little bit. Of course, it's not as easily measurable as catastrophic forgetting in a classification model, but I wonder and I suspect and I predict that we'll likely find that using RLHF maybe reduces performance of ChatGPT on a bunch of different benchmarks that aren't related to answering questions. Okay, so training a language model with RLHF involves the following 3 steps. Fine-tune a pre-trained LLM. Again, pre-training here refers to actually the meat of the training, right? It's the huge training bill, which is footed by Microsoft on a specific domain or corpus of instructions and human demonstrations. This is what the human feedback is, right? It's basically a much smaller data set which you're going to be fine-tuning your language model on. Collect a human annotated data set and train a reward model. Yep, so this is largely, I guess this is basically the same thing as this. I guess here training a reward model, what they're referring to here is probably a value function. So in reinforcement learning environments, right? So within reinforcement learning, you have these environments, and then usually there's one component of a reinforcement learning system that is usually done with a deep neural network as well, but it basically tries to approximate what's known as the value function. And the value function tries to predict what the reward is for any given state and any given action within the reinforcement learning environment. So the reward model here is potentially even another LLM, but basically what it's trying to say is, hey, if I have a data set with human questions and AI answers or LLM answers, I should be able to predict whether or not these answers are good, right? So there's a value function that tells you how good specific answers provided by an LLM are, right? Specific answers where the answers are the action in reinforcement learning terminology, and the state is the human prompt. And the reward, probably just some number between 0 and 1 that tells the large language model how appropriate its answer is. Further fine-tune the LLM from step 1 with the reward model and this dataset using RL. Yeah, okay, so once you have this reward model, right, this value function, you can then basically use that value function to kind of self-supervise might not be the right word for this, but you can use it to continue to push gradients into the large language model, right? So anytime you see the word fine-tuning, there is actually gradients being pushed into the large language model. So this is very different from in-context learning or prompt engineering. In those situations, you're not actually modifying any of the parameters of the large language model, right? So when you're doing prompt engineering, you're not really messing with the 20 billion parameters that are part of the large language model. You're really only messing with the context and the kind of like that specific instance of inference that you have created. But when you're doing fine tuning of any sort, you're actually pushing gradients into the large language model. All right, we got a nice little reinforcement learning fine tuning figure here. This looks like it's coming out of official OpenAI stuff. Yeah, and it does seem to come out of official OpenAI ChatGPT blog post. So we have step 1, step 2, and step 3, which are probably these 3 steps here. Collect demonstration data and train a supervised policy. A prompt is sampled from our prompt data set. Explain reinforcement learning to a 6-year-old. A labeler demonstrates the desired output behavior. We give treats and punishments to teach blah, 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 blah. And this data is used to fine-tune GPT 3.5 with supervised learning. So our prompt data set. So they have some data set of prompts. For something like RLHF, you'd probably want that data set to be very, very clean, right? Back in the days when supervised learning was the way that you did deep learning, the quality of your supervised learning data set, right? How many weird outliers, mislabeled instances, things like that. Like you really wanted to be careful about your supervised learning data set. And this is a similar situation here where fundamentally you're doing some form of supervised learning here where you have specific inputs and outputs that you want. So the requirement for dataset cleanliness means that this prompt dataset here that they're referring to is probably not coming from user data that they've collected, but it's probably created in-house. Collect comparison data and train a reward model. A prompt and several model outputs are sampled. Okay, so you take this prompt, you have you turn the temperature parameter to such a way that you get a bunch of different answers from the large language model. Some human labeler will rank those outputs. So they'll say, okay, this output is more appropriate, this output is less appropriate, right? So the human labeler is basically providing the learning signal for the value function, which they're calling the reward model. All right, and with that ranking, you basically create this reward model, this value function that tells you how good a specific action, which is one of these 4 answers, within a specific environment or state of the environment, which is the prompt, is. And once you have that, then you can go to step 3 here, optimize a policy against the reward model using PPO. PPO is proximal policy optimization. This is a type of reinforcement learning algorithm. This is a very, I don't want to say generic, but I want to say very basic. So pretty much any open source reinforcement learning library, such as OpenAI Gym or RL, I think it's called RL Baselines. There's a bunch of different ones, but they're going to have PPO. PPO is not a particularly complicated or niche reinforcement learning algorithm. It's actually one of the easiest ones, and it's usually the one that you try first. So it's important to note that there isn't a ton of crazy stuff that they're doing there by choosing PPO. Okay, so now that you have this value function, you have this reward model that they're talking about, you can create a new prompt, feed that prompt into the value function. PPO model is initialized. Policy generates an output. The reward model calculates the output. So here you go. The reward model will say, okay, this output given this answer or given this prompt, and then it's going to give you a score, right? It's going to give you a value. It's going to predict the reward, right? And by predicting that reward, then you can say, okay, well, I'm going to push that gradient back into our PPO model, which is the actual reinforcement learning model that's choosing the best answer, right? And then you just keep doing this over and over and over again, and you're going to be able to train this PPO model that will very efficiently, or not efficiently, that will be able to choose the best answer out of a bunch of different answers, where best is defined by the distribution of answers that these labelers have created, right? So like every time the labeler is creating a supervised kind of datum here, right? So they're saying, hey, this is the prompt, this is what the answer should be. So this is one way that the signal's coming into the system. And then this is another way that the signal's coming into the system where you have a labeler that's ranking answers. So both of these are basically human labelers shaping a distribution of what good answers should look like. And then you're training a value function to basically try to estimate that distribution, and then you're training a reinforcement learning PPO model to pick the answers based on this reward model. So there's 3 different function approximators, 3 different AIs in this. You have the reward model, you have the supervised policy, which is probably also deep learning model, and then you have the actual large language model. Choice of the base large language model is crucial here. The best open source LLM that can be used out of the box are instruction fine-tuned LLMs, notable models being Bloom. I think this one actually you can use it on HuggingFace, it's available. Flan UL2, OPT-ILML. One that they don't mention here, because I think it came out after this blog post, is Llama. So Facebook's Llama was leaked, and you can use it, and people have been doing crazy stuff with it. But it is a little sketchy, right? Because if you build a product that has Llama at the core of it, Llama technically is only should only be used for research purposes. So maybe Meta can sue you. There's a lot of uncertainty when it comes to whether or not you can use LLMs for applications without the explicit permission of the companies that train them and so on. Get a decent model, you need to at least play with 10 billion plus scale models, which would require up to 40 gigabytes of GPU memory in full precision. This is not true. Obviously, Llama, the smallest version of Llama is 7 billion parameters, and it is more than enough to play with. People are running the 7 billion parameter version of Llama on a Raspberry Pi, which is even crazier to think about. Full precision, this refers to the fact that when you're performing inference with a model, right, each of these 10 billion parameters, that's a number, right? Each of those 10 billion parameters is a number. And within programming, you can store numbers at different precision, right? You can store a number as a float 64, which means you're using 64 bits of information to store a single number. You can store a number as a float 32, which uses 32 bits to store that same number. So half the amount of memory to store the same number. And you can basically keep going down and down that. There's floating point 16, and people are now figuring out how to store numbers into basically 4 bits. That's where the limit is right now, where each of these 10 billion parameters is stored in just 4 bits of information, which is crazy to think about. What is TRL? So TRL is a library making RL step much easier and more flexible so that anyone can fine-tune their LM on their custom dataset and training setup. You can use this algorithm to fine-tune a model to generate positive movie reviews and so on. Using TRL, you can run one of the most popular deep RL algorithms, PPO, in a distributed manner on a single device. We leverage Accelerate from HuggingFace to make this possible. I wonder if they actually implement PPO themselves or whether they actually use a deep learning library externally. So let's actually do that. TRL library. Okay, that's not going to give us what we want. Do they have a link to the TRL library? I think they have one here. Where's the GitHub? Here it is. TRL. We go into the requirements.txt. They use transformers. They use Accelerate. Okay, there's no OpenAI just yet. PPO Trainer. PPO Trainer, PPO Config. Let's see. TRL models. Modeling base. HuggingFace, HuggingFace download, PEFT config. From pre-trained. Okay, it doesn't look like they're using any external reinforcement learning libraries here, but that's also why they only have PPO implemented, right? If you go to something like RL baselines, yeah, this is another open source reinforcement learning library, and these have way more algorithms, right? These have way more than just PPO. See, not only do they have PPO1, they have PPO2, they have TRPO, TD3, SAC, DQN, DDPG. These are all different reinforcement learning algorithms, right? these guys have a lot more implemented. So seems like these guys only have PPO, and the value head is basically the value function, which is the reward model. Okay, let's get back to the article here. Fine-tuning a language model with RL follows roughly the protocol detailed below. This requires having 2 copies of the original model to avoid the active model deviating too much from its original behavior. You need to compute the logits of the reference model at each optimization step. Okay. Having 2 copies of the original model. So in reinforcement learning, your data a lot of times is gathered with the model, right? So if you have some agent is a word in reinforcement learning used to describe the actual model that performs actions in an environment. So if you have a Atari game, the model that actually chooses to go left or right in an Atari game, that's called the agent usually. And in order to gather data, you need to let your agent play in that environment and play in that world. And you have your agent, you make it play in this environment, and then you get a bunch of data, which allows you to train, right? Push a bunch of gradients into the agent, and then now you have a new agent, and then you take that new agent and you can deploy that into the environment again, and so on. But the fact that you have to basically pause training while you're collecting environment data, right? Rollouts, episodes, as they're sometimes called, is annoying, right? You don't want to have to like wait for collection of environment data while you're training and so on, and like do this alternating back and forth. So there's a lot of different techniques that people have come up with where you have different versions of the model, right? Different versions of the policy that are being executed. And then you have more kind of complicated systems that people have come up with where it's how do you update all of these, right? Do you take these different copies of the model and you're kind of averaging them together and so on, and how often do you average them together and how do you average them together and so on. So here they're referring to 2 copies of the original model, right? And the reason they're doing this is that they don't want the active model deviating too much from its original behavior and distribution. Compute the logits. So logits are basically the very last layer of a neural network that outputs a distribution over actions, right? So for example, here, the action that your policy or your model could output is basically which of these 4 outputs has the highest confidence, right? Highest probability. And underneath the confidence or the probability, there's what's called the logit, which is basically just, you could think of it like the probability. This adds a hard constraint on the optimization process, as you always need at least 2 copies of the model per GPU device. Yeah, that's why usually people are doing distributed training with reinforcement learning. If the model grows in size, it becomes more and more tricky to fit the setup on a single GPU. Yeah, and if you have images, so another kind of thing about reinforcement learning is a lot of times in the literature, people use environments where the action and the state of the environment are actually very small, right? Such as in like Atari Pong, for example, right? You could say that the state space of that game is merely the position of the little, I don't know, the little paddle, and then numbers that represent basically the board. A chessboard is a very low dimensional environment, right? But as soon as you add image or any kind of images or I don't know, sound or any kind of like modality of data that is very large and has a very high dimensionality, this can blow up the amount of memory that you need on a GPU. All right, overview of the PPO training setup in TRL. So this is, I guess, how PPO works in their particular implementation here. Rollout. So this is using the This is like an episode. This is actually using your model, your policy, to take steps in an environment, right? So you're taking your query, this movie is, and then your response, and then this is your language model. So your language model consumes this query, this prompt, right? And it outputs more tokens, right? More text tokens. Evaluation query plus response. So this is where the reward model or the value function comes in, right? You're combining the query and the response, the state and the action in reinforcement learning terminology. And you're saying, okay, given this state and given this action, what does my reward model say the reward is, right? And reward doesn't have, there's no units to this. It's basically just usually a number between 0 and 1, and it's normalized such that it always comes out nice and smooth and nice and clean between 0 and 1 and so on. But the reward model says, okay, given this state and this action, given this query and this response, this is the reward. And you can imagine if it said, this movie is, and then it said, I don't know, the capital of the United States is Washington, D.C. The reward model would say, well, that response is not really relevant to the query, therefore the reward is low, right? Optimization. So once you have the query and the response, you have two different versions of the model. You have, I guess, the active model, which is the one that hasn't been fine-tuned, or the one that has been fine-tuned, right? Different versions of the model have had different gradients pushed through them. So both of those are going to output some log probability over what the next token should be, what the response should be. You want those two, or you want the probability. KL divergence is basically a metric. It allows you to compare two probability distributions and say how similar are these probability distributions. So it's very common in reinforcement learning to say, hey, my policy, right, my model is going to output not just actions, but a probability distribution over actions. And then I want that probability distribution over actions to match this other probability distribution over actions. So anytime you see KL divergence, it's basically just like a statistical concept where you can compare two distributions, but it's not commutative, and it's not quite a metric. There's a little bit more nuance if you dig into it, but at a high level, if you're not super interested in the statistics, it's basically a distance metric for probability distributions. So it'll give you the distance between basically the output of the active model and the reference model. You're also feeding in the reward there, and that allows you to policy gradients here. What it refers to is the gradients that are coming from the policy, where the policy is, this is going to be a deep neural network here, and it's going to update the model here. You can also use shared layers between reference and active models to avoid entire copies. A concrete example of this feature is showcased in the detoxification example. Okay. Training at scale. Training at scale can be challenging. The first challenge is fitting the model and its optimizer stores on the available GPU devices. The amount of GPU memory a single parameter takes depends on its precision, or more specifically D-type. So D-type is data type. This is a programming concept. Most common being float 32, right? So this is what we were talking about before. You have different amounts of bits required, right? So 32-bit required to store a float 32, 16 bits required to store a float 16, and so on. More recently, exotic precisions are supported out of the box for training. So int 8, and then I've even seen 4-bit as well. In a nutshell, to load a model on a GPU device, each billion parameter costs 4 gigabytes in float 32 precision, right? And if you go from 32 bits to 16 bits, you halve the amount of memory required to put that in memory. If you use the AtomW optimizer, so this is a very popular common optimizer. Many techniques have been adopted to tackle these challenges at scale. All right, so this is a little bit of machine learning scaling here, but whenever people do model training in a parallel way, there's a lot of different types of parallelism, right? You can have data parallelism, model and data parallelism, right? So at a high level, what these refer to is that you have the data that you're training your model on. Usually that data is basically coming in batches. So the model is training on a single batch of data at a time. And then the model itself is composed of all these different weights, right? So you could say, hey, I have whatever, each of these little squares here represents one GPU, one compute kind of node. And you could say, hey, I'm going to take my big giant model and I'm going to split it over all of my computers. And that's what's called model parallelism, where each computer, each GPU, each compute node is only calculating the math or the kind of like arithmetic associated with pushing gradients. It's only calculating it for a single little part of the model. Data parallelism says, hey, well, I'm going to put my model on every single one of these computers, but instead I'm going to split the batch of training data on all of these different compute nodes. So I'm going to have the model on all of them, but I'm going to split the data there. So maybe this first computer sees only the first 4 examples from one batch. The next computer sees the next 4 examples from one batch, and so on. And data parallelism and model parallelism at a high level, that's basically what they are, but rarely are people doing it in this most kind of vanilla basic way, right? Usually it's a much more complicated combination of both model and data parallelism that is specific to the hardware that you're training it on, right? JAX, which is a machine learning framework, is popular specifically for this, right? Where it's very good at these PMAP and then VMAP, right? Parallel mapping, different ways of basically taking your compute graph, if you want to call it that, and mapping it onto your compute that you have available, right? Mapping it onto your hardware. Data parallelism, the same model is hosted in parallel on several machines, and each instance is fed a different data batch. This is the most straightforward parallelism strategy, essentially replicating the single GPU case, and is already supported. With pipeline and tensor parallelism, the model itself is distributed across many machines. Pipeline parallelism is split layer-wise versus tensor parallelism splits tensors operations across GPUs. So this is also, how are you splitting the model itself, right? Are you basically taking the whole model and then just saying layer-wise, so I'm going to calculate the first layer, then the second layer, then the third layer, and have each of those on separate machines? Or tensor parallelism, where, hey, this layer is maybe this wide, and I'm going to take different chunks of that wide layer and split those. So even within model parallelism, there's a lot of different subtypes of parallelism. You need to shard the model weights across many devices. Sharding is basically the process of taking one big blob of data and then turning it into smaller little blobs of data that get sent to different machines. You define a communication protocol. This is not trivial, and you might need adoption of frameworks. Not trivial at all, right? This type of stuff becomes extremely complicated very quickly. You need to have a very good understanding of the hardware that you're using, of the problem that you're using, where the bottlenecks are. We have looked at some articles before that talk about this and how that's changing over time, especially as the hardware landscape changes. So initially everybody was really using NVIDIA GPUs, but now you have, of course, the TPUs, you have the Tesla Dojo chips. There's kind of an explosion of the hardware, and all of those different hardware systems are going to have slightly different bottlenecks, slightly different things, different memory, different. Some of them are going to be better at I/O. Some of them are going to be actually better at just matrix multiply. So there's a lot of different variables that go into how to take your problem and distribute it across a variety of machines. Highlight other tools, adaptive activation, checkpointing, fused kernels. So kernels are basically, you have a mathematical concept within some model architecture, and you need to turn that into code that GPU can execute at the lowest level, right? So usually the mathematical concept is converted into Python, and then that Python gets basically converted into a CUDA kernel, right? And then that kernel gets executed by the machine. So that step where you go from Python function into kernel, there's a lot of opportunity for optimization there, right? And especially if in your model architecture you have a couple different mathematical concepts in a row, different layers that are kind of doing the same thing, there's an opportunity there to fuse the kernels underneath them, right? And rather than doing 3 operations, if you can figure out a way to fuse them into a single kernel, you can get a lot of speed. So, but this type of stuff is very hard, right? Very hardcore engineers are the people that do that. Therefore, we ask ourselves the following question: how far can we go with just data parallelism? We use existing tools to fit super large training processes in a single device. The answer appears to be yes. The main ingredients are adapters, 8-bit matrix multiplication. Let us cover these topics. 8-bit matrix multiplication is a method that has been first introduced in the paper LLM-int8. So this is matrix multiplication with 8 bits numbers, which means that it's a lot lower memory, right, than if you had to use 32-bit numbers. Solve the performance degradation issue when quantizing large-scale models. Yeah, so quantization is great, right? Quantization, the process of taking these larger floating point data types and making them smaller so that you can do things faster and cheaper. The problem is that you're reducing the precision by which each of those 20 billion parameters is defined. And when you keep reducing the precision, the actual output is going to be not as good, right? You're going to have this performance degradation. So think about it. If you were calculating the area of a circle or the circumference of a circle, imagine if you had the number pi, right? 3.14, blah, 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 blah. If you had a number pi with 100 decimal places, the final answer you would get when calculating the circumference in the answer would be pretty accurate. If you were only using the number pi up until 2 decimal places, so 3.14, the final answer that you get for the area and the circumference is not going to be as good, right? There's going to be a little bit of this performance degradation. And there's a similar kind of effect that happens when you quantize machine learning models. Breaks down the matrix multiplications, the outlier hidden states part that is going to be performed in float 16, and the non-outlier part that is performed in int8. So, okay, there's different parts of the model. Some of them are going to be more susceptible to this performance degradation from quantization than others. So having different data types throughout the model might be a way to do this, which is kind of what they're suggesting here. Efficient 8-bit matrix multiplication is a method that has been first introduced in the paper and aims to solve the performance degradation when quantizing large-scale models. The proposed method breaks down the matrix multiplications that are applied under the hood in 2 stages: the outlier hidden states part that is going to be performed in float 16 and the non-outlier part that is performed in int8. Okay, so 8-bit, I guess this is the 8-bit. Multiply a 16-bit x here with a x, and you output a 8-bit x. Okay, so I don't think that this seems like a little bit unnecessarily confusing, but largely the TLDR here is that they're being intelligent about when they use 16-bit versus 8-bit numbers to save on memory and improve the amount or the size of the model that you can fit on a single GPU, or in their case, more GPUs, because they're doing this on many different GPUs probably. Low rank adaptation and PEFT. In 2021, a paper called LoRA, Low Rank Adaptation of Large Language Models, is demonstrated that fine-tuning a large language model can be performed by freezing the pre-trained rates and creating low rank versions of the query and value layer attention matrices. So what does freezing mean? So freezing the pre-trained weights is you have your large language model, right? It's made up of 20 billion numbers, and you've trained it on next token prediction for a very long time. Well, you haven't trained it, but OpenAI has trained it because they spent that money to do that. When you're fine-tuning, you're pushing gradients and changing the values of those weights. But there's another way of fine-tuning where rather than changing the values of the weights of all 20 billion of those weights, you basically freeze a large portion of those. So you basically say, okay, I'm only going to fine-tune the very top of my large language model, right? And I'm going to everything, all these other weights below here, right? The whole bottom of the iceberg when it comes to my large language model, I'm going to actually freeze those, and I'm going to prevent the gradients from actually changing those values, and that's called freezing. And you can freeze part of the model, you can freeze the whole model, you can freeze specific parts of the model, and so on. Creating low-rank version of the query and the value layer attention matrices. So large language models are based on this model architecture called a transformer. A transformer is a type of attention mechanism. And within that attention mechanism, there's these different matrices that are basically the inputs and outputs, and they're called the queries, the values, and the keys. Right? And those are matrices. So here, they're creating low-rank versions of those matrices. Right? These low-rank matrices have far fewer parameters than the original model and enable fine-tuning with less GPU memories. Okay, so basically, another way of saving on compute and saving on memory by using lower rank versions of the query and key and value matrices within the actual transformer blocks that are within the large language model. Output activations for the original frozen pre-trained weights left, okay, are augmented by a low rank adapter consisting of weight matrices A and B. So what does the math here mean? This is W, which is going to mean a matrix W. And this here tells you that the dimensionality of that matrix is D by D. So it has D rows and D columns, right? Two-dimensional weight matrix. And this fancy R just means all the real numbers in D to D. So the value of any one of those weights can be basically negative infinity to infinity, even though it's not the case. Usually it's some number between -1 and 1 that's like kind of like floating around that 0. Here you have this like fancy little script n. All that is a normal distribution centered on 0. So normal distribution is your Gaussian curve, right? Your bell curve, it's also called. So this is basically just a bell curve centered on 0. This first number is the center, and then this is the variance. So the sigma squared is basically how wide that bell curve is. Technique allows fine-tuning LLMs using a fraction of the memory requirements. The forward and backward pass is approximately twice as slow due to the additional matrix multiplications. PEFT, Parameter Efficient Fine-Tuning. HuggingFace library created to support the creation and fine-tuning of adapter layers on LLMs. Okay, so I think this is the Accelerate, probably. I think we went into their library here, and they had a Accelerate dependency here. I think that's probably what this is, if I had to guess. Support many of the state-of-the-art models and has an extensive set of examples. Token classification, sequence classification, semantic segmentation, 8-bit training, image classification. So these are natural language tasks, right? This is an image task. Conditional generation, this is a diffusion model, right? Generation, or this could actually be natural language as well, generating text conditionally on some prompt or something like that. Library is still under extensive and active development. Fine-tuning 20 billion parameter models with low-rank adapters. Note that the prerequisites are out of the way. Let's go through the entire pipeline step by step. Using the tools on a single 24 gigabyte GPU, load your active model in 8-bit precision. Okay, so you have a 20 billion model in float 32, so 20 billion parameters. If you stored all of the values for each of those 20 billion weights using 32 bits in the form of a float 32 data type, the total size of your model would be 80 gigabytes, and that is just way too big. There's no consumer GPU that has 80 gigabytes of memory. So if you use float 16, your 20 billion parameter model now fits in 40 gigabytes. So we're making progress, right? That's basically half. So what if you do half again? So now if you take those 20 billion parameters, store them as int 8s, right? Only 8 bits per weight. Now you can store all of that in 20 gigabytes. 20 gigabytes, now there are plenty of consumer GPUs that have that. It's still very expensive consumer GPUs, but they do exist. And then I was referring to the 4-bit data type. That would mean 10 gigabytes. And at 10 gigabytes, now we're talking. Now there's a huge amount, or now not a huge amount, but now there's a much broader array of consumer GPUs that could handle 10 gigabytes of memory. Free lunch memory reduction is to load your model in 8-bit precision. This can be performed by simply adding the flag load in 8-bit equals true when calling the from pre-trained method. Okay, so whenever you load a model with HuggingFace, if we go into their examples, see toxicity script. PPO config, learning rate, log with wandb. Wandb is weights and biases. Input max length, build dataset, collator, and here you go. So here's where they're actually loading the model. They're calling the from pre-trained, which will actually go ahead and grab the pre-trained model. From HuggingFace, you have to give it the name of the model, and then here is where you tell it, use the bfloat 16 version. So interesting that they use the 8-bit here, but in here they have the 16-bit. So kind of interesting. A hack to compute the amount of GPU memory is to load your model and think in terms of billions of parameters. As 1 byte needs 8 bits, you need 4 gigabyte per billion. Okay, this is just a little bit of mental math. Let's load the active model in 8-bit. Add extra trainable parameters. Okay, so we talked about how you can freeze the weights within a parameter or within a model, and that will save you a ton of time because you basically don't need to calculate the gradients and change those values of the weights. And it also means that whenever you load this model into some other computer with some other person wants to use your fine-tuned model, they don't necessarily need to load the entire model, right? They don't need to go and download these 20 billion parameters again because you didn't actually change those 20 billion parameters. All you did was you changed specifically these ones here, these orange ones, the trainable weights, right? And sometimes in the image generation world, people will refer to LoRa's, right? And that's what they're referring to. They're basically referring to these orange weights here that they fine-tune on some kind of waifu data set that they created. Load adapters inside the model and make these adapters trainable. This enables a drastic reduction in the number of trainable weights that are needed for the active model. Once adapters are trained, you can easily push them to the hub to use later. Use the same model to get the reference and active logits. Reference logits versus active logits. Okay, so earlier they were describing in the reinforcement learning section how you have two different versions of your model. You have basically the reference and the active model. And in the reference model, you haven't pushed any gradients yet. But in the active version of the model, you've updated these here, right? These gray weights, which are deactivated in the reference model, you've pushed some gradients into them. And now they're basically slightly different. They're trainable weights. They've changed. So given the same input, the reference model is going to produce something different than the active model. Logits are basically, you could think of them like probabilities, like 90% cat, 5% dog, except it's not actually percentages, it's just like a number. And you can compare those reference logits and those active logits, right? That's what they're doing up here. The reinforcement learning section, right? These are the logits. Not specifically, these are log probabilities, but the logits would be right here, right? Someone sent me a message. You have your reference model, you have your active model, and then you take those logits, they define some probability distribution, and you can take the KL divergence between those. Since adapters can be deactivated, we can use the same model to get reference and active logits for PPO without having to create 2 copies of the same model. This leverages a feature in the PEFT library with the disabled adapters. We will now describe how we trained a 20 billion parameter GPT Neo X using transformers. I wonder if these guys are still going, or are they dead? GPT Neo X. Luther AI, have they made any changes recently? 1 day ago. Okay, yeah, they're still pushing changes. Okay. 2.8 billion parameters, 12 billion parameters. These are little small models, but they're still going. Overall, there's 3 key steps and training scripts. Fine-tuning a low-rank adapter on a frozen 8-bit model for text generation on the IMDb dataset. Okay, so fine-tuning specifically only these little trainable weights. And then you're doing that on an 8-bit version of the model, right? So the most quantized version of the model, and it's mostly frozen. You're really only training these low-rank adapters, these little orange parts here. And what are you training it on? You're training it on IMDb. IMDb is like a website where you have like video reviews and stuff like that, like actors, and I think reviews as well. So like sentiment analysis is very popular, I think, for IMDb. Script, merging of the adapted layers into the base model's weights and storing these on the hub. Okay, so this is, I guess, a script for how you would go ahead and download these specific trainable weights that somebody else trained and then put them into your version of the model. So these are going to be very, very specific to the model. It's not like you can take these trainable weights from a different model and then apply them to your model. It's going to be, there's going to be a specific one-to-one kind of mapping here. You're going to need to use the exact same model that the person that did the fine-tuning uses. We tested these steps on a 24 gigabyte NVIDIA 4090. So this is pretty much the cream of the crop consumer GPU, and it has 24 gigabytes of memory available. While it is possible to perform the entire training, the full training runs were untaken on a single A100. Okay, so a little bit misleading because they were saying, hey, all of this is possible on consumer GPUs. But that's not what they did. They did it all on an A100. A100 is a enterprise kind of grade GPU. Nobody has an A100 in their house. What they do is they use A100s that are available in the cloud. And A100s have 80 gigabytes of memory in them. Trained for 1 epoch of examples from the IMDb dataset. 1 epoch means 1 entire round. So if you have a dataset, right, you train on that dataset once, that's called 1 epoch. You train on that dataset again, that's called 2 epochs, and so on. So when you see multiple epochs, like hundreds of epochs, what that means is that the model has been trained on that dataset 100 times. And here we go. Features movie reviews and indicating whether they are positive or negative sentiment. So this is whether or not a blurb of text is positive or negative. Training loss during 1 epoch of training a GPT Neo X. Important to note here that the y-axis is kind of zoomed in. So you have 2.82 is the top, 2.7. So very small change in training loss here. It's very noisy too. which is interesting. Achieved by loading the pre-trained model and adapter in floating 16-point and summary with weight matrices. We could then fine-tune another low-rank adapter on top of the frozen IMDb fine-tuned model. We use a IMDb sentiment classifier to provide the rewards for the RL algorithm. Okay, so this is the value function, I guess, that they're using is a pre-trained model that is specifically trained on sentiment classification on the IMDb dataset. And you can see here mean of rewards when RL fine-tuned. So this is kind of like your test, right? Like how good is it? So how much reward is your reinforcement learning agent getting, right? And over time, you can see that initially it's just getting about 0.5 units of rewards. Again, reward doesn't have any number or units to it. It's just like it's like a number. So 0.5 units of reward, and then you can see over time it gets larger and larger. It's getting 1 unit of reward, and then 1.5, and then so on. So it's getting better at gathering more reward. Full weights and biases report. Check it out here. Weights and biases, pretty cool company. I did work there for a little bit, but it's good for experiment tracking, and they really focus on these type of reports. Are basically like a living blog post, if you want to think of it, or like a living model dashboard, right? So you can basically have text, you can have charts, and the charts you can actually scroll through them. It is quite useful. We have implemented a new functionality that allows users to fine-tune large language models using RLHF at reasonable cost by leveraging PEFT and the bits and bytes libraries. Demonstrated that fine-tuning on a 24 gigabyte consumer is possible. Again, this is a little bit misleading because they did not use a 24 gigabyte consumer GPU. They used a A100. So we've identified some interesting directions to push the limits. How will this scale in the multi-GPU setting? Yeah, I don't think this is going to be as easy as they say it is. I think that applying different types of model and data parallelism is complicated, and it's very unlikely to me that there will be Python libraries for RLHF that abstract that away. I think you're going to need to know what the hardware is. There's going to be a bunch of different hyperparameters that you're going to have to tune in order to properly make use of a bunch of hardware, if that's what you have available. What tools can we leverage to increase training speed? We have observed that the main downside is the overall training speed. In the future, we would be keen to explore the possible directions to make training much faster. Lots of different ways to increase the training speed. One common one is just make the learning rate. But that's not great either, because then you're kind of like wiping over. Increase the batch size, use a different optimizer, do some kind of distillation. Like there's a lot of different techniques that people have come up to increase the training speed, but all of them come with their own trade-offs, and they introduce additional complexity. Cool, so that is RLHF, reinforcement learning with human feedback. I suspect that companies like OpenAI, via Microsoft, Google, and Meta will release functionality that allows you, and then like tools that allow you to do this for your specific application. So I don't know, I wouldn't necessarily go and try to learn about or learn how to use this TRL library. I think it's very likely that these type of like little bespoke libraries written by a handful of people just kind of die away, and that the big 800-pound gorillas in the room that are Google and Microsoft develop their own libraries, their own tooling to do this type of stuff, RLHF. Cool. That was a great little blog post. Thank you for listening, and see you guys later.